Another consequence of special relativity isn't just time dilation. The relativity of simultaneity, say that 5 times fast, also gives an issue when taking measurements of distance. Because if you think about something, when you measure the distance of something, you're doing 2 observations, right? You're observing how far away one end of an object is, and then you're observing how far away the other end of an object is. And depending on when you take those measurements, if that object is moving, you'll get a slightly different result. So the idea, of course, is to take the measurements of the 2 ends of the object simultaneously. But if an object is moving with respect to you, you can't take those measurements simultaneously because of, again, the relativity of simultaneity. So what ends up happening is moving objects appear shortened in the distance they're moving if their speed is a significant fraction of the speed of light. Their distances do shorten even if it's not. For example, if a school bus drives by at 25 miles an hour, it has actually shortened a little bit because of relativity. But if you calculate how much, it turns out to be about the width of an atom. So nothing that you'd be able to see. You need to have an object move at significant speeds compared to the speed of light for there to be a significant observation, a significant change in the length of an object. So like we define proper length, where it's proper time, where it's the time between 2 events that occur at the same location, right, in an observer's reference frame. The proper length is the distance between 2 points measured by an observer at rest with respect to those points. So for example, if you're on a spaceship and you're sitting down and you measure the front part of the spaceship and the rear part of the spaceship, you're moving with the spaceship, so those points don't move with respect to you, so you'll get what's called the proper length of the spaceship. However, if you're on a planet watching the spaceship fly by, the spaceship is moving with respect to you. The front end and the rear end, where you're taking those length measurements, are moving with respect to you, so you do not measure the proper length. What do you measure? Well, you measure a shortened length. It's called length contraction. Moving objects appear shorter in the direction they're moving. And how much shorter depends, again, on this Lorentz factor, gamma. So remember, gamma has to be, at best it's 1 when the velocity is 0. Gamma is 1, and the length you measure is the proper length, because if the object isn't moving with respect to you, you're measuring its proper length. If an object is moving, gamma starts to get greater than 1. When you divide something by something greater than 1, it becomes smaller. So things appear to be scrunched, but only in the direction they're traveling. So for instance, I have this square here, this t-square, right? So if this thing is moving really fast in this direction, near the speed of light, what would happen is everything, this top bar, would appear scrunched. It would appear I could smush it together and it would appear shorter. But this sidebar, it would appear thinner, but it would have the same length because this length in this direction is not moving. Right? It's not shortened because it's not moving down. If we're moving down, then this bar would appear shorter. This piece would appear skinnier, but it would have the same length. So things are only shortened in the direction they're traveling. So if a spaceship flies by, it doesn't just appear smaller in all dimensions, it just appears to be squished in the dimension it's traveling with respect to the observer. Now, again, this is just due to the fact that you are observing something traveling at a significant fraction of the speed of light. Things in the spaceship aren't really squished. For people in the spaceship, everything appears fine. Time dilation, right? Moving clocks don't really travel more slowly for the people in the spaceship that's moving because they see everything is traveling just fine. It's not like if you see a spaceship fly by, everyone inside feels squished and everyone feels like they're moving in slow motion. They notice nothing wrong. Everything appears as it should. It's just how we see other clocks move, how we see the length of other objects change depends on how its motion with respect to us. Your clock on your watch on your wrist will always tick away at the same length. A meter stick you carry around with you will always appear to be the same length, regardless of how fast you're moving, as long as those objects aren't moving with respect to you. So here's the equation for length contraction. And length contraction solves the paradox of the twins. Remember I talked about the twins paradox in the previous video about two identical twins getting on a spaceship. Oh, sorry, one identical twin getting on the spaceship, the other staying behind. Twin number one flies to the Andromeda galaxy and back, 2.5 million light years away. When they fly there, it saves some very, very, very high fraction of the speed of light. They fly to the Andromeda galaxy and back. By the time they get back, 5 million years passes on Earth. Their twin is long dead, but they have aged maybe a few weeks to a few months. Well, how's that possible? Well, for the twin on Earth, since the Andromeda galaxy is 2.5 million light years away, it takes light 2.5 million years to get there, 2.5 million years to get back. So it's not surprising that if you go there and back, 5 million years passes, and the twin on Earth is long dead. But what about the person in the spacecraft? What do they observe? They don't observe 5 million years passing. For them, and maybe a few weeks has passed. Well, for them in the spaceship, for the twin in the spaceship, the length is contracted. So rather than 2.5 million light years to get to the Andromeda galaxy, if you're traveling at an appreciable speed of light, maybe that's only a light year away, or maybe that's only a few million miles away. So the faster you travel, the closer to the speed of light you travel, the shorter the distances appear. And your book gives the example of muons, and I'll link to a video that talks about simultaneity and length contraction and time dilation from a really wonderful website called 60 Symbols, I believe, where they talk about these physics symbols, and the Lorentz factor gamma is one of those symbols. Muons are high energy particles that are created in Earth's upper atmosphere from collisions with cosmic rays, and they live very, very short lives. So short that traveling at the speed of light, they should not be able to reach Earth from the upper atmosphere. They should all die out before they can reach Earth. They see Earth in the distance, they fly towards it at near the speed of light, and according to classical physics, they should all die. They should never be able, they should decay before reaching Earth. But we detect them on Earth. How is that possible? Well, it depends on the perspective. For people on Earth, we see the muons moving at near the speed of light. We see their clocks traveling more slowly. So they live longer because they're moving at a very high speed. From the muons' perspective, they live as long as they're supposed to live, but the distance when they fly down to the Earth is contracted, so they don't have to go as far before they hit the Earth. So I strongly recommend looking at the video we have in the other additional resources material at D2L. There's a wonderful video from 60 Symbols. I'll see if I can link the website below here. I don't think I can link the video where you can click on the video, but you can type this in and it'll take you to that 60 Symbols video, which is actually quite good.